Okay, this is the last section in chapter 6. We are going to split it up into 2 days, so we'll do some today and some tomorrow. And then we'll do a little bit of practice with it on Friday and then begin reviewing for our test. Monday we'll have some in-class time where we'll do a little bit of probably an activity together again, and then Tuesday is the test. Okay. So, it's going to kind of feel that this is like a third separate idea in this chapter. Like we kind of started with oblique triangles, right? And then we moved into vectors. And now we're going to talk about complex numbers, okay? While they feel very separate, vectors and complex numbers are going to have a lot of similarities. And so a lot of the ideas that we used in the last couple of sections, you're going to see here again. Okay. So first of all, at your pod, discuss anything you remember about what a complex number is. All right, pod 1, what do you got for us?
Combination of a number and I is the square root of negative 1.
A combination of a number and I. That is exactly what it is. Okay? So A is our real piece. B is our imaginary piece. Okay. Bless you. Okay. Any number we can write as a complex number. It's basically the biggest spectrum of numbers that we have. It encompasses all of them. All right. Now, we are going to graph complex numbers, but I want you to understand that this is very different than plotting a point x comma y. Okay. When we graphically represent a complex number, we have a real axis and an imaginary axis. That we're going to use to plot our points. Okay. So if I wanted to plot the number 2 plus 3i, please always make sure that your real number comes first and that your imaginary number comes second. If your number is not written like that, you need to rearrange it so it's real plus imaginary. Okay? So we are going to graphically represent this coordinate, not this coordinate, excuse me, this number. We would move positive 2 on the real axis and positive 3 on the imaginary axis. And that would be the representation of 2 plus 3i. Okay. We are plotting on what is called the complex plane, very separate than the xy plane. Okay, so maybe I'll label that. All right, let's plot another one. How about 5 minus I? Will, how would we plot 5 minus I on the complex plane?
You go to 5 on the real axis and negative 1 on the imaginary axis.
Great. How about the number negative 3i? Connor, what would we do there?
Just go down 3.
So go down 3 and we plot that number on the imaginary axis. If I wanted to plot the number 2, Nicole, what would we have to do there? Just go over 2, and there's our number on the real axis. Okay? Now, seems kind of strange, but it actually is going to help us with the next thing that we need to determine. Okay? So, the next conversation that you're going to have, but with a partner, not everybody at the table, but just 2 people, so you groups of 3, you're going to have to talk together, okay? But partner up at your table, and I want you to discuss this. What is the absolute value of 5? What's the absolute value of 4? And what do they represent about the number? Go. Okay, Molly and Marissa, what do you think?
We said 5 and 4, and then the distance from the axis, or from 0.
Okay, from 0?
Yeah.
Yes. Okay. So 5 and 4 were their respective answers, and they said the distance from 0. How do you feel about that explanation? Okay. If we were to plot these numbers like on a number line, right? Their distance from 0 would be 5 and 4. Okay. Now, we are actually going to have to work with the absolute value of a complex number. Okay? Now, if the absolute value of a real number is the distance from 0, what does the absolute value of a complex number represent? Distance from, what did you say? Okay, go back to this picture right here. Jackson?
0, like the origin 0, 0.
Okay, so in this case, since we're on the complex plane, we're going to be at the origin, 0, 0. Okay, Dave, does that make sense? Okay. Okay. So here I have a complex number plotted, 3 plus 4i, right? And highlighted, I have what I would consider the distance from 0, right? Here's where we're going to see some familiar ideas. How are we going to find that distance? Say it. The Pythagorean theorem. To plot that point, we have to go over 3 and up 4. So we can make a right triangle. And to get that distance, we could essentially say that distance is the square root of 3 squared plus 4 squared. Do you agree? Okay. So instead of distance, that is representing the absolute value of 3 plus 4i. So the absolute value of 3 plus 4i, when we use the Pythagorean theorem, is 5. It looks familiar, doesn't it? What can we compare that to with our vectors? It's the same as the magnitude of our vectors. Okay, so if you want to write something in general here, okay, we kind of talked about it with an example. The absolute value of a plus bi is going to be the square root of a squared plus b squared. We're using the Pythagorean theorem to get the absolute value of that number. So what I would like you to do for me is find the absolute value of negative 5 plus 2i. When you have it written down, check it with your neighbors. You can leave it in radical form. Darby, what do you have?
I have radical 29.
Darby has radical 29. Do you agree? Square root of 5 squared plus 2 squared is radical 29. Okay, now the fun stuff. Let's get into some more trig. Okay? The trig form of a complex number. Instead of writing it as a plus bi, which would be in standard form, we can write a complex number in trig form. Okay. So I'm going to have you go ahead and draw this picture here. I have the number a plus bi plotted. And I have a couple of things highlighted. R is representing the absolute value of a plus bi. And theta is that angle of rotation in which we would have to rotate to get there. Okay. Does this diagram look familiar? I hope you are saying yes. Okay. So first of all, we know how to get R. Correct? Okay, R is just the absolute value of a plus bi, which would be our a squared, square root of a squared plus b squared. Okay? Once again, this should feel familiar. How do we determine theta?
Tangent b over inverse tangent b over.
Okay, so the tangent of theta equals b over a. So we can use those two ideas to figure out what r and theta are. I'm going to tell you what r and theta are here soon, so just hold on, or what we do with them. Okay? Now, if we wanted to rewrite a, and we knew r and theta, what trig function could we use to do that? We know r and theta, and we want a. Cosine, right? We know that the cosine of theta is a over r, right? So if we didn't know a, we could take r, the absolute value, times the cosine of the angle and get a. Does that look familiar? Right? Same thing for b. If we didn't know b, we could use the sine function. The sine of theta is b over r, which means r times the sine of theta is a way we could find b if we didn't know it. The trig form of a complex number. It's basically taking a and replacing it with r cosine theta, taking b and replacing it with r sine theta. Please write that down. Okay. Now you'll notice that that I is in front of the r sine theta. Typically we see the I after the number b, but when we put it in trig form, we put that I in front so it doesn't get squished in with that angle. Okay? If you put it at the end, it's not going to bother me. Like if it really is weird for you to put that I in front of r sine theta and you put it at the end, I'm not going to count it wrong. Okay? But this is the form that you're going to see. Okay. So we are going to, before lunch, we're going to work with a complex number and we're going to put it into trig form. Okay, that's what we're going to do before we go to lunch. So go ahead and write down this number, negative 5 plus 6i. In order to write our number in trig form, that means we need to find r and we need to find theta. Okay? So r is just the absolute value, which means we take the square root of a squared plus b squared. What's 25 plus 36? What? 61? And 61, I don't think a perfect square divides into that, so we're going to go ahead and leave it. Okay. Leave it as a square root of 61, just like you would in your vector days. Okay. Now, we need to know what the angle is. Now, on the complex plane, which quadrant would negative 5 plus 6i lie in? Quadrant 2. So what should that mean about our angle? It better be between 90 and 180. Exactly right. So we can still use the tangent of theta equals b over a. If it were me, I'm probably just going to put 6/5 into my inverse tangent function and not even worry about the negative. Okay. What acute angle would that give us? $50.19. Okay. So I wrote the positive number because I like to think of it as a reference angle, right? So since we're in the second quadrant, we want 180 minus that reference angle. Which means 129.81 degrees would be our actual angle. So the trig form of this complex number would be, instead of negative 5, we're going to write square root of 61 cosine of 129.81 degrees. Plus, remember the I comes first for some weird reason, I times radical 61 sine of 129.81 degrees. And that is the trig form of our complex number. It gives us what we like to think of as the direction angle and the length, the distance from 0. Okay. All right, go to lunch and we'll keep going when you get back. Keep going. I do want to point out one notation thing that you are going to notice. I am perfectly happy with this right here. But there is a shorthand, because is that a lot of letters and numbers to write? Yes, it is. There is a shorthand that the book will use. I will use it every once in a while. You do not have to if you do not want to, but you're more than welcome to. It's basically writing R, C, I, S, and then theta. So in this case, radical 61 CIS 129.81 degrees. And basically it just condenses it so you don't have to write it all. So the C is for the cosine, the I the imaginary number, and S the sine, kind of the order in which they appear in the big log form. Okay, if you want to write it like this, you're more than welcome. If you don't like it, don't use it, and that's fine. But I need you to understand that those two in red are equivalent. They mean the same thing. Okay, so now let's go the other way. Here I have a number that is in trig form. Notice how the R is factored out. Okay, you're probably going to see it like that when it is in the long form, at least from your book. The R is factored out instead of written twice, and that is fine too if you'd like to factor the R out. But here we have 3 is R and 315 is our angle. Just like with vectors, if you have a special angle, I do expect you to keep it exact. Is 315 a special angle? So I expect you to keep it exact. Okay? So if we're going to write this into standard form, this is probably the easiest way to switch forms. All we have to do is evaluate the cosine and sine of 315 and distribute that R through. Okay? So we have 3. The cosine of 315 degrees. Caroline, what is that?
I'm absolutely not.
What's the reference angle for it? 30, 45, or 60? Let me ask you this. How far away is this from 360? 45. What's the cosine of 45 degrees? Radical 2 over 2. So the cosine of 315 in the fourth quadrant would also be radical 2 over 2. The sine of 315. Zach, what is that? Yeah. Negative radical 2 over 2. Very good. So our number in standard form would be 3 radical 2 over 2 minus 3 radical 2 over 2 I. When we're in standard form, the I is going to come after the V. Okay? Now, does this feel very familiar, having just come off the vector sections? I know these are two very separate ideas, but the trigonometry involved is very much the same, okay? Which is why these are grouped together, okay? Now, we want to be able to do operations with these, okay? Let me ask you this. If I gave you something like this. Don't write it down. If I gave you something like this, what would you have to do? You'd have to FOIL it out, right? All right? What if I gave you something like this? Do you remember what you would have to do here? Okay, yeah, we would have to multiply it by the conjugate, right? We would have to multiply 3 minus 2i. Okay. Yes? Sure. Uh-huh. You were leaving? You were leaving? Okay, so you'd have to multiply by the conjugate of the denominator and multiply everything out and then simplify. We did that back in chapter 2, maybe? Chapter 2? Sounds good. Okay? A lot of work, right? At least for this one. This is like 2 multiplication problems and then you have to simplify. Okay? Now, the nice thing about trig form is it makes multiplication and division way easier. Go ahead and write down these two general trig complex numbers. So if we get our numbers into trig form, then multiplication and division is a one-step process as opposed to a multiple-step process. Okay. So here's the first multiplication. In order to multiply Z1 and Z2, what we would do is we would multiply their R values and add their angles together. And then you have your product. You multiply the R's and add the thetas. We're also going to talk about division. Does somebody want to take a shot in the dark on what division will look like? Based on what multiplication looks like? Darby, what do you think?
Add the R's and subtract the thetas.
What do you think, people? Sound reasonable? Yep. You will divide the R's and subtract the thetas. Whichever one is the numerator, that's the one that's going to come first, the R's and thetas. Okay. There's also a note down here that your angle must always be between 0 and 360. If it is not, then you need to use your knowledge of coterminal angles, which we'll go over, to rewrite it so that it is an angle between 0 and 360. So to multiply, we will multiply the R's, add the thetas. To divide, we will divide the R's, subtract the thetas. And then before we come to a final answer, we will make sure that our angle is between 0 and 360. Okay. So we're going to do two examples, and then I have some examples that you will do for me and get checked off by me here when we're done with these two, okay? Ready? Here's the first one. I did use the shorthand notation. If you don't like it, you can rewrite them as 4 cosine 120 plus I 4 sine 120, etc. If you like the shorthand, it does say some pencil lead for you. Since this is a multiplication problem, what do we do with 4 and 6? We multiply them. 120 and 315, what do we do with those two numbers? We add them, so we get 435. Is this a full credit answer? No. You ever use it? And then it went away, and yes, that hurts sometimes. Okay, this is not a full credit answer because your angle is not between 0 and 360. Okay, if you flash back to chapter 4, coterminal angles, an angle that's in the same spot, it has the same terminal side, but just a different measure. Okay, if you remember doing that, what would we have to do? What would we add or subtract to get a coterminal angle? 360. So since this is more than 360 degrees, we're going to subtract 360 degrees. What do we get when we subtract 360 from 435?
75.
What?
75.
75. And that is what we want. If you would have a negative angle, like maybe when you're doing division, you could have a negative angle, then that would be a time where you would want to add 360 to get the coterminal angle. All right, last example. We are dividing. So what do we do with 15 and 3? Say louder. We divide. Our angles 240 and 135. Gabe, what do we do with those? Subtract. So 240 minus 135 would be? That is an angle between 0 and 360, so we can be done. Now I will warn you that there are a couple problems in the book where they will give it to you in standard form. You have to convert it to trig form, do this operation, and then convert it back. So it's like a few problems in one where you can compare how you do it in standard form versus trig form. Okay? Now, to practice the essentially 5 skills that we worked on today,